Check. Check. Check, 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 check. Clearly, Hanamada? Online students, can you hear me clearly? Online students, can you hear me clearly? Clearly, Hanamada, Madine? Okay. Online students, can you hear me clearly? Only can you allow messages for online students? Allow messages for online students. Online students, can you hear me clearly? Please confirm with a message. Confirm with a message. Can you hear me clearly? Okay, nice. Yeah, so Mali, disable the Q&A and keep the chat. Okay. You sure? Okay, so the plan for today is, pay attention everyone, pay attention. So the plan for today is we are starting hydrostatics, but as I remember, we are not done with circular motion, right? Did we do centrifugal force? Yes, right? Okay, we are done with theory, but we have to do a bit more questions, okay? So the initial plan was to take a few days off, like 1 or 2 days, and do rotational motion questions, then move to hydrostatics. But I think some students are getting this for the next week's term test or something like that. So the plan has changed a bit. I did the same thing in Sunday's class. Today I'm doing hydrostatics for the whole day. And from next week onwards, I'm going to take the first like 2.5 hours for hydrostatics and the last hour for rotational motion. Okay, that's how we would continue hydrostatics and hydrodynamics. We'll take for today only. I'm going to do hydrostatics for the whole day. From next week onwards, it's first 2.5 hours hydrostatics, then final like 1 hour would be rotational motion weekly revision questions. Okay, so these weekly revision tunes and other tunes we give regarding the rotational motion, bring them every week. Okay, bring them every week, because every week we are going to do a few questions. Okay, so you have to bring the rotational motion tunes we are giving these days. We keep giving rotational motion tunes. We are gonna like keep giving them for the upcoming weeks too, and you have to bring all the tunes again and again. Okay, because I'm going to pick questions here and there. I'm going to pick the important questions. Okay, I'm going to pick the important questions and discuss every week. Okay, so I actually didn't watch the match today, but I mean the match was there, but my paper said that we won. I mean winning against Oman is not a big deal, right? I mean there was a time, I think you were in that time, right? I mean, we didn't watch matches with not even with Bangladesh. We didn't watch matches with Oman. We didn't watch matches with Zimbabwe because we know it's too easy. Like, I mean, what a dumb match to watch. Okay, now we are happy just because we won against Oman. Not a good thing. Okay, it's not a good thing. It's a bad thing, by the way. Okay, but anyways, at least we won something. Okay, we see what's happening in the World Cup. Anyways, moving forward, were you there in that time? Yes, right? That we didn't watch Bangladesh matches because it's too easy and too, like, I mean, it's just a dumb match to watch because it is too easy to win. No, right? You were watching Bangladesh matches, right? Yes, I mean, there was a time we didn't watch Bangladesh matches because it's too easy. It's a very dumb match to watch because, I mean, we are going to like score like 300. They are going to score like 100. So no point of watching like Sangakkara, Mahela, these people come and finish the match. So it's just a waste of time to watch that match. So we never watch those matches. We only watch if it is a good team against us. Now it's not like that, right? We watch every match. Okay. So moving forward, talking about fluids, just starting with an introduction, okay? Starting with an introduction. Any questions from online students? Hope you can hear us clearly. Yeah, provide the hydrostatic tubes. Hydrostatic tubes are available in the resources tab, okay? You can find the hydrostatic tubes in the resources tab, or else it will be available within like few minutes. Mali provide the tubes, okay? And in the YouTube live chat, you can find the tubes. Anyways, if it is not there, it will be available within 5 minutes. And for students in the Zoom webinar, you can find them in the resources tab in the webinar, okay? Pay attention, everyone. Stop talking. Okay. I mean, the initial part of the lesson is quite easy, okay? Because things you have already done, okay? We are going to move forward with things you have already done. What is a fluid? We are going to start with what is a fluid because it is fluid dynamics and fluid statics. That means fluid mechanics. So first of all, what is a fluid? A fluid is something that can flow. So as a result, as per that definition, okay? As per that definition, both liquids and gas, okay? Both liquids and gas are classified under fluids, okay? Because a liquid can flow, a gas can flow, right? A liquid can flow and a gas can flow. So as a result, both falls, okay? Both falls under fluids, okay? Then when we are talking about fluids, there are two main categories of fluids that we are going to discuss, okay? There's two main categories of fluid that we are going to discuss. They are, one is compressible fluids and incompressible fluids. This compressible fluid and incompressible fluid thing comes out because we classify both gas and liquid under fluids. Why? You know that usually liquids are not compressible, right? They are not compressible. Why? I mean, if you put a liquid into a container and if you try to reduce its size, it's not actually possible, right? It's quite difficult, okay? You can't compress liquids that much, okay? But if you put some gas into a balloon or a container, you can compress its size, right? You can compress its size. Why? Gas particles have the ability to get close to each other and shrink by size, right? Gas particles have the ability to get close to each other and shrink by size, clear? They have the ability to be small, clear? So this is compressible, this is incompressible, okay? Why are we classifying it in this way? Because soon we are going to do like learn some theorems, and some theorems works only for incompressible fluids, okay? That's why. So this is the main classification, okay? This is the main classification. Then starting with few very familiar terms. So the initial part is boring because we are going to discuss about the things that you already know, okay? Like what? Starting with density. What is density? Density is mass over volume, right? Mass per unit volume, clear? Density is mass per unit volume, mass over volume. Then what is the unit of this? Unit of this is kilogram per meter cube. Unit is kilogram per meter cube, the unit of density. Then talking about relative density. There's a term called relative density that we are going to learn. Relative density is density of something over density of something, okay? Density of something compared to a density of some kind of a reference, clear? What is this some kind of a reference? It may be something, some kind of a oil, some kind of a solid, some kind of a gas, anything, okay? It's density of something compared to density of a certain reference, but in our syllabus, in many cases, this reference is water. So in our syllabus, if you see the term relative density of an object, it means the density of that object. It is the density of that object over density of water. Clear? It's the density of the object over density of water. Got the idea? And because we usually know the density of water, right? What is the density of water? The standard value that we write is 1000, okay? Standard value we write is 1000 kilogram per meter cube, okay? Considered as something we know, okay? So they are not going to give the density of water in many questions because we know this, right? Okay. So moving forward, okay? Moving forward, go to exercise 1. Go to exercise 1. Let's start with exercise 1. Just let me know if you find it a bit hard to understand any of these concepts because I'm going to move faster. Because things like density you have already done, okay, in O-level syllabus. So this is not a big deal. So as a result, I'm going to move faster. So you have to inform me, at least send a cheat or inform me when I'm coming around. You have to inform me if you find it hard to understand something, okay? Because I'm going to move faster because these are very familiar concepts. Let's go to exercise 1. Question 4. Exercise 1, question 4. Question 5. Question 4, question 5. Exercise 1, question 4, question 5. Question 7 and 8. Question 7 and 8. Let's start with these questions. And online students, to get your tudes delivered, you have to join the group. Hope you are in the group. Join the group and there's a form to be filled, okay? There's a form to be filled. From that form, you can get you can fill that form and get your tudes delivered. Now, the tudes are available in the resources tab of the webinar, okay? Tudes are available in the resources tab of the webinar. And for YouTube live students, well, and tute will be available now in the groups, okay? Tutes will be available now in the WhatsApp groups, and it will be available in the YouTube live chat too, okay? Tutes will be available in, tutes are now available in the webinar resources section and in the YouTube live chat and in the YouTube live chat as a link, okay? And if you are not in the group, if you need to join the group, or if you have any issue, just contact this number, okay? 070-154-6825. And after all, if you can't still find the tute, just give a call to this number, okay? 070-154-6825. Give a quick call to this number now. And if you are not in the group, if you need to join the group, just put a message. And there's a question about the Sunday class. Sunday class, I mean, it's also an English medium class, but I usually teach in Sinhala. So the explanations are mainly in Sinhala with English terms. So that's about the Sunday class. Okay, we are going with the same schedule. Okay, Sunday class have the same schedule, same size, like entirely equal classes, and an English medium class. But I mean, I usually do the explanations in Sinhala there. That's the only difference. Okay. It's the same schedule, Sunday evening. Okay. Let's start with few questions. Exercise 1, question 4. I mean, there's question 1, 2, 3, some easy questions giving you the mass, giving you the volume, then you divide it and get the density. I don't think that's required, okay? That's why I skip those questions, okay? So, exercise 1, question 4. Density of two liquids A, density of A is 2000, 2000. Density of B is 4000. Density of B is 4000. What is the relative density of the mixture? What is the relative density of the mixture? They are asking for the relative density when equal volumes of liquid A and B are mixed. So equal volumes are mixed. So let's go with the definition for this. What is density? Density is mass over volume, right? Density is mass over volume, clear? Then mass equals volume into density, okay? Then first one, when equal volumes of A and B are mixed. So we add equal volumes, that means a volume of V from A and a volume of V from B. A volume of V from A and a volume of V from B, okay? Equal volumes. So what is the total density of the mixture? Total mass, that means mass of A plus mass of B, total mass over total volume, right? That means volume of A plus volume of B. That is the resultant density, right? Clear? The resultant density of a system is total mass, that means mass of A plus mass of B, plus total volume, that means volume of A plus volume of B. Clear? So then, in that case, what I get is, see, mass is volume into density, right? Volume into density. So I'm putting a volume of V from A. So VA is V. Volume of V from B. So VB is V. Okay? Clear? Then what is the mass of A? Volume of A is V. Volume of A is V. What is the density of A? It is 2000. Clear? It is 2000. 2000 plus. Then what is the mass of B? Mass of B is, volume of B is V. Volume of B is V. What is the density of B? 4000. Clear? Density of B is 4000. So this gives me the total mass of B and total mass of A. Then V cancels out. Then I get 2000 plus 4000. Here 1 plus 1, that means 2. 2, which gives me 3000, right? Which gives me 3000 kilogram per meter cube. Kilogram per meter cube. It gives us 3000 kilogram per meter cube. That's how we go with the definition properly. Okay, I saw people writing this plus that divided by 2. I know, like, you most probably you may have got this answer, right? Okay, but still go with the proper definitions. Okay, go with the proper definition. See, I mean, I know you got the answer directly without going through all of this stuff, but still try to go with the definition. Okay, then it's quite easy. Nothing could go wrong. Okay, nothing could go wrong in this method. Okay. Question 2. Question 2. Second one. When equal masses of liquid A and B are mixed. Okay. Now we are mixing equal masses. So just go with the definitions. How? I'm going to put a mass of M from A. I'm going to put a mass of M from B. See? Equal masses from A and B. Okay. It's an equal mass from A and equal mass from B. Clear? An equal mass from A and equal mass from B. Okay. So equal masses from A and B. So here again total density is total mass over total volume. Okay, total mass is mass of A and mass of B. Total volume is volume of A plus volume of B. So now again from this definition, volume is mass over density, right? Volume is mass over density. Clear? So I'm putting a mass of M from A, mass of M from B. We are putting a mass of M from A and mass of M from B. Then what is the volume of A? Volume of A is mass M over volume of A is M over density of A, right? Density of A, clear? So what is the density of A? 2000 plus mass of B is M divided by density of B, you get the volume of B, right? You get the volume of B, clear? So what is the density of B? It is 4000. So M cancels out again. M cancels out. You get, this is 1 plus 1, which is 2 over 1 over 2000 plus 1 over 4000. You have to solve this. Okay. 1 over 2000 over plus 1 over 4000. And they are asking about the relative density. Okay. So if it is relative density, you divide this by 1000. That's all. Okay. So they are asking the relative density. So how do we get the relative density? To get the relative density, you get the density. You get the density and divide it by the density of water, 1000. You divide it by the density of water, 1000. Then you get 3. No units. Okay. Density over density, no units. No units for relative density. Okay. Then here also, what is the relative density? Here also the relative density is divided by 1000. Divided by 1000. So what is the answer? 2.6667. Well, And some ask like the match is happening in February last week ideally. This is February, right? Yes, right? So the match is, pay attention, match is happening February last week. Have no idea about the location. Lot of locations are booked at the moment, but we'll somehow manage it. Yeah, in the last week. So there's a Google form available in the group to fill your teams, okay? If you can't find 11 people, just fill it with 6 people. If anyone can't find 11-person teams, you'll go with 6-person teams, okay? We'll see, okay? We'll see how things get aligned by then, but it will be the last days of O-level ideally, okay? As per the plan for now, it would be the last days of O-level, and for the people who are, people who don't play cricket are also welcome, okay? Because even I can't play cricket properly, so no big issue. There would be some other stuff happening too. As you requested, like a party and a DJ, it's essential for anything, okay? So, yes, be there even if you are not playing cricket. The days will be informed, but fill the Google form, the people who are playing cricket, okay? Who are the people who are capable of playing cricket? Who are the people who are capable of playing cricket? See what has happened to our country? See, now you see why we don't have a good national team, right? See, those days, if we ask who can play cricket, the whole section can play cricket, okay? So who can play cricket again? If you think you can play cricket, see how can we have a national team then? If it is not working, let's convert it to a football or a rugby match, something like that, okay? We'll decide by then, or we'll decide on the day morning, okay? On the day of the match, on the morning, we'll decide what is the game we are going to play, okay? If anyone's not, if a team from our batch come, you guys going to lose anyways, okay? Because our people were better, okay? So in the morning we'll decide on the match day. In the morning we'll decide if it is whether it's cricket or something. So for now, let's call it just a match, okay? It may be American football or some kind of a harmful something. That's what you need, right? Okay. Moving forward. So it's going to be February last week, Monday, or February last week, Thursday. You have O-level holidays on those days. If it is Thursday, it's going to be the last day of O-levels, as I think. And if it is Monday, it's a poor day. Okay. So we'll see. Okay. Exercise 2, question 3. When the volume of A is double that of B. So A, volume is V. From A, volume is B. Sorry, from B, volume is V. From A, volume is 2V. Okay. From B, volume is V. When the volume of A is double that of B. This is volume of B. Volume of A is 2V. Okay. Clear? We are putting double the volume of A as B. So now it's quite simple. Definition of density, mass over volume. Pay attention. Definition of density, mass over volume. So mass is mass of A plus mass of B. Then total volume is volume of A plus volume of B. What is mass of A? It is volume of A, which is 2V into density of A. What is the density of A? 2000 plus what is the volume mass of B? It is the volume of B, which is V, into what is the density of B? It is 4000. Density of B is 4000 over VA plus VB. Okay, over VA plus VB. VA is 2000. VA is 2000 plus VB is 4000. Sorry, VA is V. Sorry about that. VA is 2V. VA is 2V. Volume of A is 2V. Volume of A is 2V and volume of B is V. Clear? Clear? So just go with the plain definition, okay? No shortcuts. Just go with the plain definition, okay? Then you have a good idea about what is happening. Then later when you're comfortable, you can go with shortcuts, okay? Clear? So V cancels out. V cancels out like this. Then you can do the calculations. 2000 into 2 plus 4000. 2000 into 2 plus 4000 over 3. 2000 into 2 plus 4000 over 3. So we are getting the same answer as I see. 6.67. So next part I'm not going to do it the same pattern, okay? It's the same pattern. You take M and 3M, then do the calculation, okay? Last part. I'll quickly write that. When the question 4, I'll quickly write that. When the mass of A is 3 times the mass of B, that means from A it is 3M, from B it is M, okay? So what is the density? Overall mass 4M, overall mass 4M, mass from A is 3M, mass of B is M, so overall mass is 4M. Then volume of A, 3M over density of A. What is density of A? 2000, pay attention. Then what is the volume of B? M over density of B, 4000. You solve this, you get the answer, okay? You solve this and you get the answer. Clear? Just go with the definitions. Next, question 5. Question 5. Density of water is 1000. Density of water is 1000. Density of water is 1000. The volume of air bubbles dissolved in water is 1 over 10 of 1 meter cube of water. That means in 1 meter cube of water, actually it's not all water. 1 over 10th of it is air, okay? It is air. Then find the density of water with air bubbles. Find the density of water with air bubbles. So it is, anyways, density is still mass over volume, okay? Density is still mass over volume. Let's take 1 meter cube of water. Okay? In 1 meter cube of water, it's not all water. 1 over 10 is air. So other 9 over 10 is water, okay? So in 1 meter cube of water, how can I get the mass of water? Actual water. Mass is density into volume. Pay attention, stop talking. Mass is density into volume. Then density of water is 1000, right? Pay attention. Density of water is 1000. Density of water is 1000. And what is the volume? For 1 meter cube, it's 9 over 10 of 1 meter cube. Clear? It's 9 over 10 of 1 meter cube. That's how much of water, how much water you have in 1 meter cube. Clear? This is the amount of actual water in 1 meter cube multiplied by the density. Clear? Then you get what? Then you get a total mass of 900. 900. So the actual mass is 900 kilograms in 1 meter cube of water. Sorry, it's 900. So what is the answer? It's 900 kilogram per meter cube. It's 900 kilogram per meter cube. Write this down. 900 kilogram per meter cube. Question. Find the number of dissolved air bubbles in 1 meter cube if volume of air bubble is 2 millimeter cube. So it's quite simple. How? Number of air bubbles means total air volume over the volume of a air bubble. Total air volume over the volume of a air bubble. So total air volume is 1 over 10th of 1 meter cube, right? It's 1 over 10th of 1 meter cube. That means 1 over 10th of meter cube over volume of air bubble is 2 millimeter cube. So 2 into 10 to the power minus 9 of meter cube, right? 10 to the power minus 9 of meter cube. Clear? Okay. Millimeter cube into meter cube. Okay. Solve this, you'll get the answer. Okay. So it is 10 to the power 9 over 10 to the power 9 over 20. Solve this. Okay. And I mean, if you are capable of moving forward, just finish. You can even finish exercise, I think 2, 3, and I think until the end of exercise 4, you can finish. Okay. I can't rush fast, but from the knowledge you have from all levels, you can finish until exercise 4, but there are students at different levels. That's why I'm explaining these things. Otherwise, we don't have to explain these stuff. These stuff were done in all levels. Okay. But I'm explaining these things because, I mean, I can't skip just because it's in all levels. I can't skip things. Otherwise, if you did things well in all levels, you have the ability to finish until exercise 4. Do that. Okay. You don't have to listen. Okay. Just finish until the end of exercise 4. Okay. Yes, anyways, online students could come, okay? Everyone is invited. I mean, I don't even know who's in my class or not. I mean, actually, in this class, okay, I got a Sysygy English medium physics class. There's overall 550 students paying, okay? So there's a lot of students only for this class. Okay, got to see this class. There's overall 550 students paying. Some from Jaffna, some from Ringo, some from Colombo, and we sometimes deliver tubes to Delkanda. Okay, there are people joining online from Delkanda. Okay, there are people watching online from Delkanda. Okay, we categorize to online students as students who join online and watch recordings. We have several students who are watching recordings from Delkanda, and we have several students like joining live from Delkanda. Okay. So, I mean, people who are watching recordings, understandable, most probably they have a different class. But the people who join online live from Delkanda, I don't know. Okay. So, yes, everyone is invited. So, online doesn't mean far away now. Okay. Uh, Question 7. Question 7. Question 7. Given two liquids of relative densities D1 and D2, D1 and D2, given two liquids of relative densities D1 and D2, find the relative densities of liquid mixtures obtained by mixing equal masses of two liquids. Find the relative density of liquid mixtures obtained by mixing equal volumes of two liquids. Okay. Pay attention. Stop talking. Okay. So, relative densities of liquid mixtures obtained by mixing equal masses. Equal masses. D1. So first, equal masses. So let's take again the same scenario. You put mass of M from this and mass of M from this. Then what is the density? What is the density? So they are giving relative densities. Okay, we have to be careful about that. They are giving relative densities. So I'll take D1 material as 1, D2 material as 2. So if it is relative density is D1, its actual density is D1 into 1000, right? If this one's relative density is D2, its actual density is D2 into 1000, right? Okay, clear? Why? Relative density into density of water, you get the actual density, right? Relative density into density of water, you get the actual density, right? Okay, so it is D1 and D2. Find the relative densities of liquid mixtures obtained by mixing equal masses of two liquids. So I put M from 1, I put M from 2. So what is the density? Density is M1 plus M2 over V1 plus V2. It is M1 plus M2 over V1 plus V2. Clear? So what is M1? M1 is D1 into 1000. Sorry, M1 is, this is the density. So M1 is M. I'm putting a mass of M from material 1. Then what is M2? I'm putting a mass of M from material 2. What is the volume? You can get the volume by dividing mass by density, right? Volume is mass over density. Clear? Clear? So to get the volume of V1, you divide this mass M by the density of 1. What is the density of 1? 1000 D1. 1000 D1. Clear? Then again, mass of volume of 2, mass is m and divided by density of 2. What is the density of 2? 1000 d2. Density of 2 is 1000 d2. Okay. So m cancels out. M cancels out. You solve this. You solve this. Then you get 10 to the power 6 d1 d2. When you solve this, you get d1 plus d2, d1 plus d2 over 1000 d1 d2. 1000 d1 d2. Then what is the relative density? Relative density is density over density of water, which is 1000. Density over density of water, which is 1000. So 1000 d1 d2 over d1 plus d2, then 1000. So you get what? d1 d2 over d1 plus d2. d1 d2 over d1 plus d2. Clear? Did I make any mistakes? Yes or no? Yes? Oh, really? Well, there's a 2 here, right? Okay. There's a 2 here. So it's going to be 2000. Clear? Got the idea? I mean, you don't have to do this, okay? I'm just making things correct. Did I still make a mistake? No? Okay. Pay attention. Pay attention. So, I mean, you don't have to do this, okay? Multiplying things by 1000. You can directly go with relative densities and still get the answers, okay? I mean, we just multiplied everything by 1000, then at the end, divided everything by 1000, okay? That's all. Clear? We multiplied everything by 1000. Then at the end, we divided everything by 1000. That's what we did, right? So you actually don't have to convert, but I mean, I did that just to make everything correct, okay? Then these intermediate steps are correct. Because you can't get a mass by multiplying by relative density. You have to multiply by density, right? So you don't work with relative densities. You convert things into densities first. Then mass is mass, volume is mass over not the relative density. You have to divide it by the proper density. Then only at the end, to get the relative density again, you divide it by 1000. Okay. But what actually happens is you are dividing everything by 1000 and multiplying everything by 1000 and divide everything by 1000 at the end. But if you go with relative densities directly, these intermediate steps are wrong. You can't divide mass by relative density and get anything. It doesn't mean anything, right? When you divide mass by relative density, it doesn't mean anything, right? When you divide mass by density, you get the volume. When you divide mass by relative density, it doesn't mean anything, right? Clear? Okay. So, I mean, these intermediate steps are correct because I converted things into densities. But if it is an MCQ or something like that, no one cares about steps. So directly go with the relative densities, okay? Clear? Okay? If you don't need the intermediate steps, directly work with relative densities, okay? Because what actually happens is you multiply things by 1000 to get density from relative density. Then at the end, you divide things by 1000 again to get relative density, clear? You should have worked directly with relative densities, okay? Got the idea? Question? Okay. Okay. Mixing equal volumes of two liquids. So same thing. It is 1000 D1 and 1000 D2. 1000 D1 and 1000 D2 equal volumes. So what is density? M1 plus M2 over V1 plus V2 equal volumes. That means volume V from both. Volume V from both. So it is V plus V. It is V plus V. Here what is M1? V into 1000 D1. V into its density. Then what is M2? V into 1000 D2. 1000 D2. Then V cancels out. V cancels out. You get 1000 D1 plus D2. 1000 D1 plus D2 over 2. Then to get the relative density again, you divide things by 1000. You divide the density by 1000 or the density of water to get the relative density, which means 1000 D1 plus D2 over 2 and another 1000 here. Another 1000 here. Clear? It's 1000 D1 plus D2 over 2 and you divide it by another 1000 here. Then you get what? D1 plus D2 over 2. D1 plus D2 over 2. That is the relative density. Got the idea? Again, in this case also it's useless, right? You multiply things by 1000 and at the end you divide things by 1000. That's all. Clear? Question 8. A sphere whose volume is 200 centimeter cube has an air hole. The mean density of the sphere with this hole is 200 kilogram per meter cube. If the density of the medium in which the sphere is made is 3000, find the volume of the air hole inside the sphere. Okay, let's try that. Let's try question 8. Question 8. Question 8. A sphere whose volume is 200 centimeter cube. 200 centimeter cube has an air hole. It has an air hole. The mean density of the sphere with this hole is 200 kilogram per meter cube. Kilogram per meter cube. If the density of the medium in which the sphere is made is 3000, this material is 3000, find the volume of the air hole inside the sphere. They need us to find the volume of this air hole inside the sphere. Let's call it V1. So what is the actual density? Sorry, what is the actual volume? 200 centimeter cube. Okay, 200 centimeter cube. So this is the idea. I mean, what is this 3000? 3000 is the actual material density. What is this 200? For someone who measures things externally. Externally in the sense the person somehow get the radius and get the volume and get the mass from a balance, then divide them and get the density. Clear? He don't know about the whole and all. He just get the total mass and divide it by the total volume and get the density. Clear? So that is the idea. So here, in this case, what we can do is, just write the equation. What is the equation? Density is total mass over total volume. Total mass over total volume. Then, total volume is 200 centimeter cube. Total volume is 200 centimeter cube. So 10 to the power minus 6. 200 centimeter cube. Clear? What is the total mass? What is the total mass? That I can get like this. What is the actual material volume? I'll call that Vm. What is the actual material volume? Actual material volume is 200 centimeter cube minus V1, right? I write V1 in centimeter cube. Then 200 centimeter cube minus V1, right? Clear? That is the actual material volume. Clear? Then what is the actual material mass? It is volume into density, right? It's volume into density. Clear? Volume into density. So what is the volume? 200 minus V1 in centimeter cube. So convert it to meter cube, multiply by 10 to the power minus 6. Okay, this is the actual material volume into actual material density 3000. Clear? This is the actual mass. Other part is air. Okay, this is the actual mass. Actual material volume, which is 200 minus V1 into 10 to the power minus 6 to convert things into meter cube into actual density of the material. Clear? Then you put the actual mass here. Okay, you put the actual mass here. Okay, then what is the density? What is the relative density? Relative density is 200, right? The mean density of the sphere with this hole is 200. Actual density. Actual density in the sense the density you are getting from outside. Okay, that means total mass over total volume. So you solve this, you get V1, okay? You solve this. Only unknown in the equation is V1. We see what is V1? So we are getting 186.67, right? V1 is volume is 186.67. Centimeter cube. Centimeter cube. Clear? Okay, let's move forward. Okay, let's move forward, and at least send a chat if you need me to explain anything again. Okay, let's move forward. Okay, pay attention, everyone. Pay attention. Last rows, pay attention. Okay. Now, next topic, pressure. Something you again know. Okay, but I have to explain according to the syllabus. Okay, what is pressure? Pressure is force over area, right? Pressure is force over area. Okay, pressure is force over area. Then, it's the force acting on unit area. Okay, it's the force acting on unit area. Okay, and perpendicular to it. Okay, that means if there's a, it's actually a average value of force, something like that. That means if you have a certain area, if you have a certain area of A, if you have a force F like this, if this angle is theta, pressure is the perpendicular force, the force that is perpendicular to the system, which means here in this case it's F cos theta over area. Okay, it is F cos theta over area, force into cos theta over area. Clear? So in this case, like, why do we need F cos theta? Because we are talking about the force that has an impact on that area. So if we take this as a general force, okay, if we take this as a general force F, if I break it into this component and this component have nothing to do with this area, right? It's not actually acting on that area, right? It's just passing the area like this. Okay, if I break this force into two components as this and this, okay, this component actually don't have an impact on this surface, right? Here, it actually don't have any impact on this surface. Okay, only this perpendicular component have an impact on this, right? Clear? Only this perpendicular component have an impact on this. Clear? So that's why we consider the perpendicular force over area. Clear? That's why we get the perpendicular force over area. So again, what is the unit? Newton per meter squared. Unit is Newton per meter squared, which means actually pascals. Okay, which means pascals. Okay, so we measure pressure usually in pascals. Okay, got the idea? Okay, so next, ideally we have to do an exercise, but before moving into that, I'll finish the next part too, which is fluid pressure. Fluid pressure, that means talking about pressure, talking about fluid pressure mainly. Okay, there are two types of pressure that we can analyze. Okay, there are two types of pressure that we can analyze. What are they? What are these two types of pressure? What are these two types of pressure? One is, okay, one is the pressure by the momentum difference. That means, yes, pressure is just a general term. General term in the sense, when I apply a force like this, it creates a pressure. Okay, it's just force over area. Okay, pay attention. It's just the total force over area. Clear? It's just the total force over area. But when it comes to fluid pressure, fluid means both gas and liquid, right? Now fluid means both gas and liquid. Okay, so if it is both gas and liquid, especially when it comes to gas, okay, there's a special way of them creating the pressure. How? Take gas particles. Okay, even liquid particles do this. Okay, they just don't stay like this, right? Okay, what do? They move fast. They don't stay there. Okay, they don't stay there. gas particles and liquid particles, what they do is they move really fast here and there, okay? They move really fast here and there, okay? The gas particles around us, they are not stationary, they move really fast everywhere, okay? Then what happens, okay? Then what happens when they collide with the wall? They collide with the wall and bounce back, right? They collide with the wall and bounce back. In this collision, there's a momentum difference happening, right? There's a momentum difference happening, clear? There's a change in momentum happening, clear? Then this change in momentum over time creates a force, right? We know that rate of change of momentum is force, right? Rate of change of momentum is force, clear? So when gas particles go here and there, and when they do collisions, they create a force, and when you divide this force by the area, it creates a pressure, clear? Clear? Gas particles move really fast here and there, they collide and bounce back, they collide and bounce back, which creates a force. That force divided by the area, gas creates a pressure like that, and even liquids do this to a certain level, okay? Clear? That's usual gas pressure. If you take a tank, a small container, put gas into that, that's what happens here, okay? That's what happens here, okay? Clear? But now, another thing that happens is, pay attention, another thing that happens is, another way of pressure is, when it comes to liquid and huge gas volumes, like what? Our atmosphere. Our atmosphere is made out of gas, but it's a huge volume, right? It's a huge volume. So when it comes to liquids in containers or somewhere, when it comes to liquids, okay, and huge gas volumes like our atmosphere, okay, huge gas volumes like our atmosphere, okay, they create a pressure by their weight. They create a pressure by their weight. That means if a person is here, if we consider this point, there's a huge volume of gas above this point, right? Clear? Clear? This huge volume contains a weight. This huge volume contains a weight. Due to this weight, a pressure exerts here, right? Clear? A pressure appears here due to this weight. An entirely different type of pressure, see? So there are two ways of pressure. Initially in the lesson, what we are going to do is we are going to analyze this. Only in heat lesson we analyze that pressure, okay? Only in the lesson heat we analyze this pressure, okay? We ideally analyze this pressure in our syllabus, in hydrostatics, okay? Because liquids usually create pressure in this way, okay? Clear? By their weight, okay? That's what you later derive as H rho G, okay? So, if I take a liquid like this, okay, if I need to find the pressure at a level of H, if I need to find the pressure here, something I could do is I can draw a cylinder like this, okay? I can draw a cylinder like this with an area A, okay? Then what is this total volume? What is this total volume? This total volume is A into H. Clear? This total volume is A into H. Clear? That is the total volume. Okay? A into H. What is the mass of this part? What is the mass of this? Volume into density. Volume into density gives you the mass, right? So that means AH into rho. Clear? Then the weight created by this volume is mg, right? Clear? That's what felt by at this point, right? So if I need to find the pressure here, what I could do is, it feels this whole weight, this area feels this whole weight mg, okay? And we divide it by this area, okay? We divide it by this area, clear? The whole weight mg, whole weight mg divided by the area. Clear? Clear? So what is the weight? Mass is AH rho. Mass is AH rho multiplied by G. Clear? mg divided by A. Clear? mg over area. We get what? Pressure equals H rho G. Clear? We get the pressure as H rho G in this case. Clear? That is the pressure of the system. Okay? Then talking about an actual system, okay? Talking about an actual system, what is the total pressure here? If this is a river or a lake, what is the actual pressure here? Usually the actual pressure here is, here you feel the atmospheric pressure P naught, right? Here you have the atmospheric pressure P naught. Atmospheric pressure is felt at the atmosphere, right? Clear? Atmospheric pressure is felt at the atmosphere, right? Then it plus H rho G, okay? If you consider the overall pressure at a practical system, the overall pressure is this pressure, atmospheric pressure, plus the additional H rho G. Clear? Overall pressure is the atmospheric pressure plus the additional H rho G. Got the idea? So, how it changes with the height? How the pressure changes with the height? At zero height, it starts at atmospheric pressure. At zero height, it starts at atmospheric pressure. Then from there, it keeps increasing. Clear? It keeps increasing from there. Okay? We start at the atmospheric pressure. Then from there, it keeps increasing. It keeps growing. Okay? Clear? So, there are some properties. There are some properties of this liquid pressure. Okay? There are some properties of liquid pressure which you have already learned in the O-level syllabus. Okay? What are these properties? This actually don't have a specific direction, okay? Okay? I mean, everything is in your book, okay? You have to go to page 4. Now I'm in page 5, okay? Now I'm in page 5. Everything is included in your note. This stuff is written in page 4. Now I'm moving to page 5. So, page 5, what are the properties of these liquids or liquid pressure? What are the properties of this liquid pressure? They are, one is, if the pressure here is H rho G, that doesn't mean any direction, okay? That means it's just there, that pressure is there. It have the ability to appear in any direction. That means if you place an object in this direction, like this, a force will act like this. If you place a surface like this, a force will act like this. If you place a surface like this, a force will act like this. That means the pressure at this point is H rho G, doesn't mean any direction. It's acting in all the directions. Clear? Clear? It's acting in all the directions. Clear? It's acting in all the possible directions. Okay? So, the direction of the pressure depends on what is the placement of the surface. Okay? What is the placement of the surface? That means pressure value is just there. In all the directions it's acting. Clear? If you place a surface like this, pressure will act perpendicular to that. If you place a surface like this, pressure will act perpendicular to that. So there's no any specific direction for this. Okay? Clear? There's no any specific direction for this at this point. So, we can't consider it as a proper vector in this case. Okay? Moving forward, the pressure does not depend on the liquid shape. Okay? It does not depend on the shape of the system. What is the meaning of the shape of the system? If we take a system like this, okay? If it is a system like this, okay? Or a system like this. Or a system like this. whatever the shape, okay, whatever the shape, you have the same pressure here, okay. If the liquid level is H, clear? It does not depend, it does not depend on the shape of the liquid column, clear? If it is the same height, H rho G, H rho G, H rho G, okay, clear? So it does not depend on the liquid shape, okay, clear? That you had in O levels, right? Clear? It does not depend on the liquid shape. Whatever the shape, if it is H rho G, it's still H rho G, clear? And in a connected liquid, at the same level, you have the same pressure, okay? In a connected liquid, pay attention, in a connected liquid, at the same height, you have the same pressure. You have the same pressure. That means this liquid system is connected, right? This liquid system is connected. Then at the same height, you have the same pressure everywhere, okay? Then at the same height, you have the same pressure everywhere, clear? So if I ask you a question like this, okay? If I ask you a question like this, if I ask you a question like this, now take a container like this, area is A, and take a container like this, area is A. Take a container like this area is A. This area is A. So it's the same area at the bottom, okay? It's the same area at the bottom. Write this as an answer, maybe in a some kind of a piece of paper, try to write the answer. I need the explanation, scientific explanation. If we fill water to the same height, the weight of the liquid column creates the pressure, right? In this case, it is H rho G. In this case, it is H rho G. In this case, it is H rho G. Clear? But here you have a very small volume. Here you have a volume. Here you have a very large volume. How can three different volumes, that means three different weights of liquid, how can three different volumes or three different weights, three entirely different weights of liquid create the same pressure at the same area? I mean, ideally it's the weight over area, right? Ideally it's the weight over area, right? Clear? How can we have the same pressure when this has a very large weight of water and when this has a very small weight of water? Clear? Okay, write the answer, write it. Why am I asking you to write some stuff? Because sometimes you know the answer, but you don't know how to write it using scientific terms. This is not a question like that. I just need you to write, okay? And another thing, roughly 200 to 250 people like write the paper. Okay, but it's not enough actually. I mean enough in the sense if you are going to some kind of a paper class, it's okay. But the thing is, don't stop writing the paper. Okay, whatever the marks you get, keep writing the paper, because sometimes some people stop writing the paper when they don't get enough marks. But keep writing the paper. Okay, because we have like overall like close to 800 or 900 English medium students, okay, in this batch. But from that, online and physical, and from Gampa, Sysygy, from everywhere, from Ratnapura, from everywhere, we have close to 800, 900 English medium students. Out of that English medium students, I think close to 250 or 300, okay? Close to 250 or 300 students write the paper. The problem, but I encourage you to keep writing the paper, because like we try to keep the paper competitive as much as possible. That is one of the main reasons I teach Sinhala medium, because like after a while, when we start revision classes for Sinhala medium, second shy students means people who have done things properly, things are over, now they are doing it for the second time, so they have a better knowledge than you guys. So when we start Sinhala medium revision classes, Sinhala medium revision students, second shy students and good Sinhala medium students start writing the paper. That's why I usually keep the discussion in Sinhala and English both, not entirely English, because in a paper class, we need the Sinhala medium students and English medium students both in, because otherwise how can we see a competition? You don't get English medium results and Sinhala medium results, okay? You get results, okay? You get results. You don't have English medium intake and a Sinhala medium intake, okay? You don't have English medium intake and a Sinhala medium intake, it's an intake, okay? So I need to bring as many Sinhala medium students as possible, people who do work properly. Every year it happens, a lot of good Sinhala medium students usually write our paper. And when we start the Sinhala medium revision classes, all the second shy students, okay? Second shy students have, they are already at a B or somewhere like that, they only need to work and go for A. So they have a better knowledge level than you guys, okay? So Sinhala medium revision students come and start writing the paper. So the competitiveness of the paper goes up, okay? So we always need Sinhala medium students in the paper class to create a better competition, okay? To create a better competition, because in the English medium, I don't think that we have any huge competition out of this class, okay? I don't see that kind of a competition, okay? So, but there's a quite good Sinhala medium students, okay? So keep writing the paper, the competitiveness will keep increasing, okay? Later Sinhala medium students come and the second shy students come. Usually we don't have second shy English medium students. It's a very low count, okay? All the good second shy students are from Sinhala medium. So they'll start they'll start writing the paper, then the competitiveness would go up. You have to compete with them, okay? We can't stay in a tiny bubble of English medium students and perform and think that we are going to get a good mark. No, it's not going to happen. It's an intake. And intake doesn't mean English medium or Sinhala medium. It's just an intake, okay? So we can't just stay in a tiny bubble and think, okay, I'm the first of this class and okay, I'll be okay. Or you can't just pay attention, everyone. Stop talking. Middle row, stop talking. Okay, so you can't just stay in your tiny bubble and even in your English medium classes, you can't just perform and think, okay, I'm good, okay? You have to always compare yourself with the English medium students, Sinhala medium students, everyone. You have to compare yourself with the whole section, okay? Clear? That's why we always try to bring all the Sinhala medium students into the class. Revision students, I always encourage the revision students to write the paper, because revision students are usually better than you guys, usually, because they have done the syllabus one time, okay? So competitiveness keeps increasing, then it's much difficult to perform, okay? Then it's far more difficult to perform. So now you have to start and keep growing. Then when the revision students start writing the paper, you can compete with them, okay? Otherwise, you can't compete with them, okay? And if you can't compete with them in the class, you can't compete with them in the A-level exam, okay? Same story. So now start writing the paper, okay? Keep writing the paper continuously. Within 5 months, revision students start coming to the class. Then to compete with them, to get good marks against them, you have to be performing very well, okay? So start writing the papers now, keep growing. Then when revision students start writing the paper, you can keep competing with them, okay? Otherwise you have to give up that, okay? You have to keep that competition, okay? Have to keep that competition, because whether you like it or not, it's a competitive exam, not like O-levels. O-levels, everyone could get 9 A's, no harm, okay? Here it doesn't happen, okay? This is a competitive exam. Only a small percentage of students would get into good universities, okay? Only 6% of the country would get an A. So this is a competitive exam, okay? So start writing papers now and keep writing the paper no matter what is the mark you are getting, okay? Let's move forward. Okay, this one, what is the reason? Pay attention, everyone. Pay attention, stop talking. Last rows, pay attention. Okay, what is the reason? Because the wall is handling the rest, right? The wall is handling the rest. That means, take this shape, this one has a huge weight, okay? This one has a huge weight. Clear? So in this system, the walls feel a pressure from water, right? Clear? The pressure force is always perpendicular. So here, water creates a pressure on the wall like this, okay? Water creates a pressure on the wall like this. In this case, water creates a pressure on the wall like this. Clear? In this case, water creates a pressure on the walls like this. Clear? In this case, water creates a pressure on the walls like this. Clear? Clear? In this case, water creates a pressure on the wall like this. Water creates a pressure. Water always creates a pressure perpendicular to the wall, okay? Water always creates a pressure perpendicular to the wall, okay? Clear? Now, the reaction of it, okay? The reaction of it, when we create a force like this, okay? The reaction of it will act in the opposite direction, right? Clear? The reaction of it will act in the opposite direction. Every action has a reaction. Clear? Every action has a reaction. So the reaction of the pressure force, the liquid creating on the wall, acts like this, right? So in this case, the reaction, the wall creates the reaction, okay? Wall creates the reaction. They will act like this. Clear? Now see this reaction, okay? Now see this reaction. Only focus here, zoom here. Now see this reaction. They have upward components, right? They have upward components and horizontal components. See? Clear? From this side also they have horizontal components and upward components. All these horizontal components will cancel out. Why? See, there's a horizontal component in this direction, there's a horizontal component in this direction, right? So all these horizontal components will cancel out as a result of this surrounding nature, clear? As a result of this surrounding nature, but there will be a resultant upward force left, right? There will be a resultant upward force left. Got the idea? There will be a resultant upward force left. Clear? So when you add these all upward forces, okay, the wall will be creating an additional upward force. Clear? Wall will be creating an additional upward force. So now, if this additional upward force is F, now this bottom won't feel the full weight. Bottom will feel only mg minus this F. Clear? Bottom will never feel the full weight. It is the weight minus this force. Clear? It's the weight minus this force. Here wall have nothing to do. Why? wall isn't creating any vertical components, clear? Here wall isn't creating any vertical components, clear? So it's here, it's just the weight, clear? Here wall will be creating a downward resultant, see? Here wall will be creating a downward resultant. A downward resultant like this, clear? Clear? That means it is mg plus f, clear? In this case it is mg plus f, clear? Here it's just mg, here it is mg plus f, here it is mg minus f. So what actually happens is the wall manages the additional weight, clear? Wall manages the additional weight, so the bottom feels the same weight at the end, clear? Bottom feels the same weight at the end because the additional weight is handled by the wall, clear? Got the idea? Okay, if you need you can write it down. Let's move to questions. Exercise 2, question 3, question 4, question 5, let's start with these 3 questions. Exercise 2, question 3, 4 and 5, but if you are capable, finish the whole exercise, okay? Finish the whole exercise. Exercise 2, question 3, 4 and 5. Quickly try to get the answers. Quickly try to get the answers. Send a chat if you need me to explain anything again. And again, everyone, like, now it's the time to start working properly, okay? If you were not working properly, just try to be at least honest to your parents' money, okay? That's a message, very important. Now the having fun time is over, okay? Because I mean, soon, I mean, after A levels, you are going to go through a financial, emotional roller coaster, okay? Because you're now, I mean, like the parents get old, after a certain time you have to take care of them, you need money for that, you are going to enter a very difficult financial world, okay? So like it's not really simple as you think, okay? Now you are just, I mean, having food by your parents' money, okay? It's not a big deal. Life seems very easy. So you are just having fun. You are not being very serious enough. Okay. You are not being very serious enough. You are not working properly. But I mean, your parents are assuming that after spending on you guys for these 2 years, then their work is done. Okay. That's what your parents think. Okay. They are assuming that after spending whatever the money they have for these 2 years, then the burden from you guys are done. Then you will be working properly. You will get into a good degree. You will do that properly. You'll get a good job. They need to get out of this burden as fast as possible. That's what they're expecting. Okay, clear? So just try to be truthful for their money. Okay, just don't act dumb. That time is over. Getting the mobile phone, looking into the mobile phone in the class time, taking calls and all. Okay, not listening to things properly, thinking that acting like you don't care, you're not into, you don't need good marks, you don't care about the subject, acting like that and hoping that it is cool. Okay, clear? Coming late after the interval so that people see you and like you can look cool. Or stop all these dumb stuff. Okay, stop all these dumb stuff. Time for that is over now. Okay, now I don't speak about this for the first 6, 7, 8 months that you figuring out who you are. Okay, but after the first 8 months, now the next 26 batch is close to A levels. That means now it's time for you guys to start working properly. Okay, so stop acting dumb. Okay, stop acting dumb like you have, yes, if you have all the money in the world, as I explained last week, yes, just don't disturb others. Feel free to sleep the whole day. Okay, if you are very rich, I know that it's not a big deal for you. Okay, but for the people who are not like that, okay, for the people who are not like that, people who after some time, people who have to take care of their parents, people who have to earn their own money, people who need to like build their own future, they take things serious. Okay, take things serious. Now start working full time. Okay, every second matters. Okay, every second matters, because not everyone is dumb as some of the people here. Okay, so people keeps working. Okay, people keeps working. Okay, so they are gonna pass you very fast. Okay, then there's nothing you can do about that. They never stop working. Okay, so now it's the time to take things serious. Okay, don't act dumb. Okay, if your friend is acting dumb and asking you to behave cool, okay, clear, please explain to them. Okay, please explain to them what is happening. Okay, so be serious. If definitely it depends on you. Okay, based on your everything is not fair for everyone. Okay, if you are super rich, if your parents are super rich, if you have a career like that, if you have a business running your family business, if your plan is to like run that, yes, feel free to do that. All you have to do is do not disturb others. That's all I'm expecting from you if you are super rich. Okay, life is not fair for everyone. But if you have to get something out of A levels, if you have to build a career, okay, if you have to get something out of A levels, be serious about it now. Okay, it's the time to be serious about A levels now. Okay. Exercise 2, question 3. Exercise 2, question 3. An object of mass 1000 kilogram is placed on a horizontal surface. So first we are talking about a horizontal surface. Okay. First we are talking about a horizontal surface. Okay. It's 1000 kilograms. Find the pressure exerted on the surface when the surface X collides with the surface. So first it's like this. Okay. So the weight is 1 into 10 to the power 4. 1 into 10 to the power 4. And the area is 0.2 meter squared, 0.2 meter squared, 0.2 meter squared. Find the pressure exerted on the surface when the phase X collides with the surface. So it's the total weight over this area, right? It's the total weight over this area. Pressure is force over area, okay? Pressure is force over area. Force is 1 into 10 to the power 4. 1 into 10 to the power 4. Force is 1 into 10 to the power 4. Area is 0.2 meter squared. Area is 0.2 meter squared of pascals. That's all, okay? That's all. Then when you keep it in the other direction, when phase Y is down, when phase Y is down, okay, 1 into 10 to the power 4, then 2 meter squared, 2 meter squared. So the pressure is force over area, force over area. Same force, weight is 1 into 10 to the power 4, force is 1 into 10 to the power 4. Again, area is 2 meter squared, okay? Area is 2 meter squared. So you solve this, you get the answer in pascals. Next, both 1 and 2, I'll just do 1 when the surface is 30 degrees to the horizontal, okay? When the surface is 30 degrees to the horizontal. Okay, so this is the system. Here the area is 0.2 meter squared. So weight acts like this, 1 into 10 to the power 4. Weight acts like this, 1 into 10 to the power 4. If this is 30, this angle is 30. If this is 30, this angle is 30. So pressure is force over area. Pressure is force over area. Clear? So, now we always get the perpendicular force, right? This is the perpendicular component. Clear? This is the perpendicular component, which means it's mg cos 30 now, right? Perpendicular component is mg cos 30. That means 1 into 10 to the power 4. 1 into 10 to the power 4 cos 30. Cos 30. Okay, 1 into 10 to the power 4 cos 30 over area, which is again 0.2 meter squared of pascals. Question 4. Question 4. Pay attention, everyone. A pipe of cross-sectional area 20 centimeters squared, area 20 centimeters squared, emits water with a speed of 20 meters per second. Emits water with a speed of 20 meters per second. Density of water is 1000. Density of water is 1000. It's 1000 kilogram per meter cube. Okay. When a plate is placed perpendicular to the stream water, find the pressure exerted on the plate by the collision of water stream. At the end of the question, they tell, assume that the water moves down the plate after the collision and the cross-sectional area of the water column is constant up to the collision. Okay, so what is the meaning of this? So now there's a plate like this. Pay attention. There's a plate like this. Water column continues like this. Water column continues like this. Okay. It continues like this. Okay. So now it's change in momentum over time. You have to get the force, right? Using change in momentum over time, you have to get the force. That means idea is if this area is A, you find the force here, divide it by area, you get the pressure. Okay. So how do we get the force? What happens to water droplets moving? What happens to the water droplets moving? They move with a velocity v. They move with a velocity v. Okay. Then they become stationary and fall along the wall, right? That means the velocity of water droplets go from v to 0. Clear? Pay attention. Velocity go from v to 0. Clear? That's a change in velocity, which means a change in momentum. Change in momentum. Okay. So the total force is total change in momentum over time. Okay. So I'll use a method like this. Okay. I'll use a method like this. I'll do everything for time t. Okay. How much of water, what is the amount of water collides with the wall within time t? What is the amount of water collides with the wall within time t? Velocity of the water is what? V. So in time t, water will travel a distance of vt, right? Velocity into time. Velocity into time is the length, right? Velocity into time is the length. So in time t, water belongs to this length will collide with the wall, right? Clear? And if this area is A, what is the volume that collides with the wall within time t? What is the volume that collides with the wall within time t? It is the length Vt. It is the length of the water column colliding with the wall Vt. It is the length into area. This is the volume of water colliding with the wall within time t. Clear? Clear? Then how do we get the mass of water colliding with the wall? You multiply the volume by density. Clear? So the volume is Vt into A. You multiply it by what? You multiply it by density. Clear? You multiply it by density. Clear? So So this is the mass of water colliding with the wall. Clear? This is the mass of water colliding with the ball. Clear? In time t. Now what happens to this mass of water? Their velocity goes from v to 0. Clear? So that means what is the change in momentum? Delta mv. What is the change in momentum? Delta mv. Change in momentum is the change in momentum, delta mv is change in momentum, delta mv means mass into velocity difference, which is v minus 0, right? Velocity goes from v to 0, right? So velocity difference is v minus 0, clear? Velocity difference is v minus 0, clear? This mass, velocity goes from v to 0, clear? M v minus 0, that is the change in momentum, right? Mass into change in velocity, that is the change in momentum. So what is the force? Force is delta mv over t, right? Force is delta mv over t, clear? So what is the mass here? This, right? This is the mass, clear? V T A rho, that is the mass, clear? Then here you have v minus 0, velocity difference, clear? Divided by the time. What is the time? Time is capital T, right? Clear? Time we considered is capital T, right? Clear? That is capital T. So T cancels out, then we get what? A rho v squared. We get A rho v squared as the force. Clear? We get A rho v squared as the force. Clear? Then what is the pressure? Pressure is force over area. Clear? Pressure is force over area. Okay? So this is the force. A rho v squared. This is the force. Okay? What is the area? Area is A, right? Clear? They are telling that cross section of the area keeps constant. They mentioned that at the end of the question, right? So that means the area of collision is also A. Clear? Area of collision is also A. Clear? So you divide it by the same area A. Okay? Then A cancels out. A cancels out. You get what? Rho v squared. You get rho v squared. Clear? So this is the pressure. This is the pressure. Clear? Now we just have to substitute the values. What are the values? This is water. So density of water is 1000. Density of water is 1000. And what was the velocity? It was 20 meters per second. This is the answer in pascals. Clear? This is the answer in pascals. Clear? Got the idea? I'll keep it there. Focus there. Focus this whole part, including this. So why is the length is Vt? Why is the length is Vt? I mean, what is velocity? What is velocity? Length over time, right? Velocity is length over time. Clear? Then what is length? Velocity into time. Clear? What is length? Velocity into time. Clear? That is the length of the water column that collides with the wall within time t. Clear? Clear? Just let me know if you have any questions. Try the next part. We have to convert it into oh no, I don't have to convert things into centimeter squared. I think everything cancelled out at the end, right? Sorry? No, what actually happens is water goes with a velocity of v. water goes with the velocity of v, then they are telling that when after colliding with the wall, it goes to 0, right? So the velocity difference is v minus 0. They are telling that water goes with the velocity of v, okay? They are telling that the water goes with the velocity of v. At the end of the question, after part 1 and 2, they mention, assume that the water moves down the plate after the collision. Moving down the plate means it hits the wall, velocity reaches 0, so it just moves down the wall. Clear? So what actually happens to the velocity? Pay attention. What actually happens to the velocity? It goes with a velocity of v, then reach a 0 velocity. Clear? Then reach a 0 velocity. Clear? Water collides and goes to 0 after the collision. Clear? So what I'm trying to find is the force at the collision. What I'm trying to find is the force at the collision. Clear? So it goes from v to 0 after the collision. All this water collides with the wall, then stops and goes down. Clear? Water does not bounce back. That's what they mention. Okay? Otherwise, the answer is different. Try the next part. Any other questions? So question 8 of exercise 1, I'll explain again, okay? I'll explain again question 8 of exercise 1 because few students asked that, okay? Only provide the tute again. Tutes are available in the resources section and in the group too, okay? They are available in the resources section of the webinar. You can find a tab called resources. You can get the tutes from that, okay? So the next part, pay attention. Question 2. If the plate is inclined 30 to the east, this is 30 to the east, I think. So now pay attention, stop talking. So now in this case, okay, in this case, like what actually happens is quite different, okay? The areas changes and all, okay? What actually happens is quite different, but what they are expecting us to, I mean, pay attention, last rows. So what they are expecting, okay? What they are expecting in this question is, okay, just to get the force component of the system, that's all, clear? That means it's the same change in momentum happening to the same amount of liquid, clear? Yep. It's to the, I mean, I just actually didn't think about that much. What is actually east is right. So it's 30 to the east. I mean, just take the components. I don't even know what is 30 to the east. Okay, let's take this as 30 to the east. Okay. Okay. No big issue there. Okay. Pay attention. So now, it's 30 to the east, not we moving it 30 to the east, but anyways, it could happen in A levels or in our papers. Things should be mentioned properly, okay? I'm just taking the component, that's all. That means in this case, pay attention, last rows, stop talking. So in this case, what is happening is, I mean, it's not a very serious question, but actually if we try to consider what is practically happening, it's quite complex. But otherwise, it's just the same force, but when you consider the liquid particles, what happens to them is they move like this, then stops. Clear? That's all. So the change in momentum happens in this direction, okay? Change in momentum happens in this direction, clear? Water particles go like this, then stops. So change in momentum happens in this direction. That means force acts in this direction, okay? That means the force acts in this direction, clear? But to get the pressure, we have to get the component, clear? To get the pressure, we have to get the component. What is this? If this is 30, this is 30. If this is 30, this is 30. Then this is 60, right? Clear? So now the pressure is the same force cos 60 over area, okay? Clear? Clear? That means it's the previous pressure into cos 60. Okay? Is the previous pressure into cos 60. Clear? What was the previous pressure? Rho v squared, right? Previous pressure was rho v squared. Rho is 1000. rho is 1000, velocity is 20, 1000 into 20 squared into cos 60 means half. Clear? Cos 60 means half. Clear? So it's not a very serious question, just asking you to get the component. But if we think practically, what is happening is a bit complex. Okay? Clear? In this, pay attention. In this case, what we are actually expecting is collision happens horizontally. Collision happens horizontally. Same amount of water, same velocity difference, everything is same. Only thing is, since the surface is inclined, when taking the pressure, you have to take the perpendicular component of the force. Clear? So it just brings a new cos theta to the previous pressure. Clear? It just brings a cos theta to the previous pressure. That's what we were expecting when giving the question. But I'll do another question, much practical, considering how the area changes and all. There are a few turbine related questions like that. Then we'll be considering what actually happens, okay? How the area changes, what happens to the area of impact, like that. It's a broad subject, okay? But for now, this is what we expected, okay? That's all. Question 5. Question 5. Pay attention. So now based on this idea, you can try question 5. I'll teach one small part before giving the interval so that you can try this in the interval. So now you know the concept, right? Now you know the concept, so you can try question 5. I'll explain after the interval. I'll start by explaining exercise 1 question 8. Some students have asked that again. So after the interval, I'll start with exercise 1 question 8. Then move to exercise 2 questions. Question 5 and 6, okay? For now, I'll do one small part so that you can try exercise 3 also. Pay attention everyone, stop talking. So now, talking about the atmospheric pressure, it's the same story, okay? I'm referring to page 5. Talking about the atmospheric pressure, it's the same story. There's a huge atmosphere which acts as a huge liquid column. Pay attention. This is a huge atmosphere which acts as a huge liquid column. Okay. So as a result, even the atmospheric sphere creates a pressure of H rho g. Okay. Since it is a huge air column. Okay. I mean, usually gas pressure. Gas pressure, we don't use H rho g usually. Why? It's just particles colliding here and there. Otherwise, a gas column can't create a lot of pressure, right? A column of gas can't create a lot of pressure because they have a very small density. But only when it comes to atmosphere, it's a huge gas column, right? Clear? It's a huge air column. Clear? So as a result, it can create a pressure of H rho G, okay? It can create a pressure of H rho G, okay? So moving forward, so to measure atmospheric pressure, we use pascals, and it is very close to 1 into 10 to the power 5 pascals. It is very close to 1 into 10 to the power 5 pascals, okay? But when it comes to pressure, and especially atmospheric pressure, we use a very specific unit called mercury centimeters to measure the pressure, right? Why? Because of the barometer. What is barometer? An instrument we use to measure the pressure, atmospheric pressure. What is barometer? We fill a glass tube with mercury. We fill it completely, then put it into a mercury filled basin. Okay, clear? Now what happens when you put it into a basin of mercury? The mercury level will go down. But since it was filled entirely, when mercury level goes down, any gas can't enter here, right? Because it was filled entirely. When I put it like this, the mercury level goes down, but this is empty. Nothing can enter here, right? Which creates a vacuum here. That means pressure here is exactly zero. Because a vacuum can't create any pressure, right? A vacuum can't create any pressure because this pressure is a zero. Clear? This pressure is a zero. Okay. Now, what is the pressure here then? If this mercury column is H, pressure here is H rho G. H rho G, rho is density of mercury, H is mercury height, G is gravitational acceleration. Clear? Now, when this is H rho G, it is the same liquid and the same level of the same liquid have the same pressure. Clear? Same level of the same liquid have the same pressure. Got the idea? Okay. So if the pressure here is H rho G, here also it is H rho G. Clear? But here it is in contact with the atmosphere. So this point have the atmospheric pressure too. Clear? If this point is connected with the atmosphere, here you have the atmospheric pressure. Clear? So this atmospheric pressure is equal to the pressure here, which is H rho G. So I can use this system to measure the atmospheric pressure. Clear? Since we use mercury for many calculations related to atmosphere, it's just useless to get H and multiply it by rho G and get an answer. So we introduce a new unit called mercury centimeters. That means instead of getting H and multiplying it by rho G and giving answer in pascals, without doing this, we just give the direct answer as H. Okay, this is mercury centimeters. That means you just use the height of mercury to represent the pressure instead of converting it by multiplying with rho G. Clear? Which is quite convenient, right? Clear? Usually, the mercury column that balances with atmospheric pressure is 76 mercury centimeters. So ideally, to give the answer in pascals, what you have to do is you put 76 mercury centimeters here, multiply by the density of mercury, multiply by G, and write the answer in pascals, which is a lot of work. Instead of that, what we do is we just tell pressure is 76 mercury centimeters. Then if someone need to convert it to pascals, they know what to do. You get that height, multiply it by density, multiply it by G. But still you can use mercury centimeters as a unit. Got the idea? Clear? So, after question 5 and 6 of exercise 2,
question 5 and 6 of exercise 2. Okay, you have to move exercise 3, pay attention, exercise 3, question 2, part 1, 2, 3, and question 4, 1 and 2, and question 7. And question 7. Try these questions after the interval. Be here exactly by 6:20. Start doing these questions, okay? Start doing these questions. I'm going to explain things. I'm going to start explaining. I'm going to start explaining things at 6:20. Try these questions. Exercise 2, question 5, 6. Exercise 3, 2, 4, and 7. Only focus here. Only focus here.
Check. Okay, moving forward. I'll start with the questions. Exercise 2, sorry, exercise 1, sorry, exercise 2, question 5. Exercise 2, question 5. A plate of surface area 100 centimeters squared is placed vertically. Small spherical spheres collide with a rate of 400 sec per second, perpendicular to the surface with a velocity 20, and bounce off with a velocity of 10. If the mass of one sphere is 5 grams, what is the mean force on the surface due to the collision? Find the pressure exerted on the plate. So there's a plate like this, area 100 centimeters squared, area 100 centimeters squared, 5 gram particles, move towards the wall, goes with a velocity of 20, then returns with a velocity of 10 after the impact. Pay attention, stop talking. Returns with a velocity of 10 after the impact. Okay, returns with a velocity of 10 after the impact. Then 400 per second. 400 spheres per second, okay? It's 400 spheres per second, okay? If mass of one sphere is 5 gram, what is the mean force on the surface due to the collisions, okay? So, again, let's do the calculations for time t. Pay attention, stop talking, last rows. Let's do the calculations for time t, okay? Calculations for time t. So, what is the mass colliding per time t? It is 400 per second, okay? It is 400 per second. Pay attention. It is 400 particles per second, okay? 400 particles per second. So, 400 into t, this is the number of particles colliding in time t, clear? It's 400 particles per second multiplied by time t, okay? And what is the mass of one particle? 5 grams. Mass of one particle is 5 grams. That means 5 into 10 to the power minus 3 kilograms. So this is the total mass colliding per second, clear? This is the total mass colliding per second. Rate into time, you get the number of spheres colliding, multiplied by the mass of one sphere, which gives you the total mass colliding per time t, clear? Now what is the force? Force is delta mv over t. So initially I didn't mark the direction. I didn't consider what is positive, what is negative. I didn't go into that direction. Why? It was anyways v minus 0, right? It was anyways v minus 0. I was only considering about the magnitude, okay? Because at that point it was only v minus 0. So I didn't think about what is the positive direction, what happens first, after that what happens, what should be the direction of the positive velocity. I didn't think about that because it anyways goes from v to 0. So I just wrote v minus 0, okay? I just wrote v minus 0 because I just needed the magnitude of the force. Here I have to be careful. Why? Ball goes with a velocity of 20, returns with a velocity of 10. Clear? Ball goes with a velocity of 20. After that it returns with a velocity of 10. Clear? So I have to think about what is happening. So here I have to properly choose a direction, okay? Here I'll choose this direction. I'm finding the force acting on the balls, okay? I'm finding the force acting on these spheres, okay? So in that case, I'm choosing this as the positive direction. What is the mass colliding in time t? This, right? This is the mass colliding in time t, clear? 400 t, 400
400t, here 5 into 10 to the power minus 3. 400t and 5 into 10 to the power minus 3. Here? So this is the mass colliding in time t. What is the velocity difference felt by these particles? What is the velocity difference felt by these particles? What is difference by definition? Pay attention. What is difference by definition? It is final velocity minus initial velocity, right? By definition, difference means final minus initial, right? Clear? By definition, difference means final minus initial. So, final velocity of these particles is 10, right? Final velocity of these particles is 10. Initial velocity of these particles is 20. Clear? Final velocity is 10. Initial velocity is 10. Okay? So, final velocity I write as 10. Pay attention. Final velocity I write as 10. Okay? What is the initial velocity? Initial velocity is 20. But this is my positive direction. See? This is my vector positive direction. Stop talking, everyone. Stop talking. So the positive direction is this, right? So this 20, it is in this direction. This is my chosen direction. So this should be written as minus 20, right? Clear? So final velocity minus initial velocity. But initial velocity 20 should be written as minus 20. Clear? Initial velocity 20 should be written as minus 20, not 20, right? Clear? By initial velocity 20 is in this direction. This is my chosen direction. Got the idea? Okay. Divided by the time I considered is capital T, right? Time I'm considering is capital T. Clear? Mass, velocity difference, which gives me the change in momentum, divided by the time. Rate of change of momentum means what? Force. Clear? Clear? I mean, actually what is happening is it's overall 30 velocity difference, right? Going in 20, then returning with 10. Overall, it's a velocity difference of 30, right? Considering the directions, okay? Initially, I didn't mark the direction. No, I didn't do anything like that, okay? Initially, I didn't mark the directions or didn't do anything. Why? It's anyways go to 0. So I just wrote v minus 0. Here, I can't do it like that, okay? I have to be proper. So, t cancels out, then you solve this, you get the answer. This is 30, this becomes 30. So what is the force? $400 into 5 into 30, 60 newtons. This gives us 60 newtons. Another thing, okay? Pay attention. Now I'm doing this question properly. So pay attention. What is this 60 newtons? I think I did the calculation properly. Did I write everything properly? Yes, right? Okay. So pay attention. What is this force that I calculated? It is not the force on the wall, okay? It's the force on these spheres. That is the force felt by the spheres, okay? By the change in momentum of the spheres, what I get is the force appearing on the spheres, not the wall, okay? So what I got here is the force acting on the spheres, okay? But they are asking the force on the wall. But the reaction of this force is on the wall, right? Clear? Whatever the force created on the spheres is created by the wall. So a similar and opposite reaction will act on the wall, right? Clear? So the same force 60 newtons is acting on the wall, okay? So that is the proper way. Initially I didn't think about that, okay? Now I'm doing it properly, okay? So initially also what we calculated was the force on the water, but reaction of it is acting on the wall. Clear? Reaction of it is acting on the wall, okay? So here also I use the velocities of the spheres, which means I'm getting the force on the spheres, okay? But the reaction of it acts on the wall definitely. Clear? Got the idea? Reaction of it acts on the wall. So So the force on the wall is also 60 newtons, okay? Force on the wall is also 60 newtons. So it's ideal in a essay paper, if you can do this, then write a statement, reaction of this force is acting on the wall, and write this, then it would be a perfect answer, clear? Okay, if you can write those steps in a essay paper, I mean, sometimes the marks won't be allocated for that statement, okay? Marks won't be allocated for that statement, okay, because it's too much to allocate marks for that kind of stuff, okay? Because very less number of students consider these things properly. But still, when you write that the person who marks your paper in A levels, they know that what you're talking about, okay? They know that you know what you're talking about. So there's a high possibility of they marking your paper with a proper attitude, okay? Yeah, that matters, okay? Anyways, the personal preference and the attitude matters in A levels, okay? That means what the person who's marking the paper, what they think about you matters. And that's why, like, there are very intelligent students who get very good marks at term tests, okay? Sometimes get low marks in A levels because their writing is not that nice. Sometimes they skip steps. Your class teacher knows that you are good because you usually ask questions from them, the conversations goes on. So your class teacher usually knows that you are skipping steps because you are intelligent, so you don't need the steps. Your class teacher knows, although you are not writing things neatly, you are very good. So these personal preferences tend to give you more marks in the term test. When it comes to A levels, it's only an index number, okay? No personal preference there. So the personal preference grows based on your handwriting, okay? Personal preference grows based on how neat you are writing the paper. Personal preference grows on how are you considering the proper physics. When you write these kind of statements, that, I mean, this personal preference of your class teacher about you grows through direct interaction, right? Clear? But when it comes to A levels, only way of creating a positive personal preference about you is by writing these kind of statements of explaining proper physics. You write few statements like that at the beginning, the person marks your paper with a proper attitude, then you tend to get more marks, okay? So, like the people who don't write things neatly, the people who skip steps, okay? People who don't think about writing things neatly and don't work on their handwriting, okay? You are in a huge trouble when it comes to A levels, okay? You are not going to get the same marks you are getting in term tests, okay? You are never going to get the same marks, same level of mark that you are getting in the term test, okay? Because you are getting good marks in the term test due to a certain amount of personal preference. Even in your paper classes, the same thing happens. After a few weeks, people know you, people know your name, okay? People know whether you are a good performing or a bad performing person. So based on that, your marks depends, okay? So for very good people, very intelligent people, people who understand things properly, they get good marks in class papers, they get good marks in term test papers, school term test papers. But all of a sudden, they get bad marks in A levels. If they come and ask why, what is the reason? But the reason is that, why? The personal preference is, it grows on the A level paper, it grows only by the index number. Index number have nothing to do. So on your handwriting, how neat you're writing things, and based on the steps and the statements you write in the paper, okay? Clear? So growing a better personal preference matters, okay? Clear? So that's why, otherwise these statements are unnecessary, but it's good if you can write. The reaction of these forces acting on the wall, then you continue, okay? Clear? So moving forward, next they're asking the pressure, okay? Next they're asking the pressure. So the pressure is force over area. Force is 60 newtons. What is the area? Area is 100 centimeter squared. 100 centimeter squared. Okay. Area is 100 centimeter squared. Clear? So you solve this, you get the answer. (60 over 100 into 10 to the power minus 4). 60 over 100 into 10 to the power minus 4. It's 6,000 pascals. It's 6,000 pascals. Let's go to exercise 3, question 2 and 4 and 7. So here also ideally change in velocity is not v minus 0, it is 0 minus v, okay? I didn't think about that in that question, okay? Because I only needed the magnitude, okay? Clear? Okay. So still it's in the board, I'll explain, there's a request to explain this. I mean, this is not a very major question. I mean, what actually happens here is a bit different, okay? So in this case, okay, pay attention. In this question, like what we expected was something simple. It's the same flow of water. Same thing happens to the water. They go with a velocity of 20 and stops. Same thing happens to the water. So the force acting on the water is same like before. Force acting on the, pay attention, force acting on the water is same as before. Clear? Then definitely the force acting on the wall is also same as before. But only thing is they are asking the pressure. When they are asking the pressure, what we need is the perpendicular force, right? What we need is the perpendicular force. So the same force, you have to get the cos 60 component. Clear? Same force, but you have to get the cos 60 component. You have to get the perpendicular force, right? Clear? So it's the force into cos 60. Clear? Which makes force of area the same pressure you got in the initial one, but into cos 60. Clear? Clear? So that is the only difference. Okay? Okay, moving forward, pay attention. Okay, I'll come to that later. Okay, pay attention. Here, question 2, it is 40 centimeters here and another 40 here. This angle is 30. This angle is 30. This angle is 30 in the second one. And in the third one, this is the first one, second one, then the third one. Okay, pay attention. Mercury is also present in the tube placed in a mercury vessel. What is the pressure at the gas trapped in the tube? So they are asking the pressure in the gas trapped in the tube. Okay. So in this case, what is happening? It is the atmospheric pressure here plus the H rho g, right? Here. What is the pressure here? Pay attention. It's the atmospheric pressure here, P naught. Atmospheric pressure here, P naught, plus the H rho g, right? Clear? Plus H rho g. But if I try to convert things into pascals, it's a lot of trouble. So what I would do is, it's anyways mercury, right? It's anyways mercury. So the pressure by this 40 centimeters of mercury can be directly written as 40 mercury centimeters, right? Clear? It's anyways mercury. So pressure by this 40 centimeters of mercury can be anyways written as 40 mercury centimeters, right? Clear? It can be anyways written as 40 mercury centimeters directly, right? Clear? So don't have to go through the trouble of converting things into pascals. I'll write the atmospheric pressure here as 76 mercury centimeters. Then I'll write the additional pressure by this mercury column as 40 mercury centimeters. Okay. Then we get direct answers. Clear? Then we get direct answers. Okay. So I don't have to go through the trouble of converting things into pascals. Okay. So it's 76 plus 40, which gives me 116 mercury centimeters. Unit is 116 mercury centimeters. Clear? Okay. It's easy to go with mercury centimeters. Okay. Then here also the same story. Same story. Here the pressure is P naught plus the pressure by this mercury equals the pressure here. Okay. But in this case, pay attention. But in this case, pressure is, as you know, in H rho g, H means the vertical height always, right? In the equation H rho g, H means the vertical height, right? H means the vertical height, right? This. Clear? This is H, okay? In the equation H rho g, okay? So, here it is 76 mercury centimeters atmospheric pressure plus not 40 sine 30, right? Vertical height of this is 40 sine 30. So now it is 40 sine 30, which means 76 plus sine 30 means half. Sine 30 means half, so that means 20. So we get 96 mercury centimeters. We get 96 mercury centimeters. Clear? Okay. Moving forward, pay attention. Here the pressure is P naught. So the pressure in the tube is equal to P naught, right? Why? No vertical height of mercury. No vertical height of mercury from here to here. So it's the same pressure, or else I can tell pressure at the same level of the same liquid is same, right? Pressure at the same level of the same liquid is same. Clear? So if this is P naught, this is also P naught. Clear? So that can be written as 76 mercury centimeters directly. 76 mercury centimeters directly. Okay, pay attention. Pay attention. Here, now the gas is here, right? The trapped gas is here. So in this case, it is pressure here. In this side, it is pressure plus H rho G plus H rho G. That is equal to atmospheric pressure in this case, right? Here you have the atmospheric pressure, clear? Here it's the pressure in the tube plus H rho G equals the pressure in the atmosphere. This side is open, right? Clear? So in this case, pressure in the tube is P naught minus H rho G. If I write in mercury centimeters, it is 76 mercury centimeters minus the vertical height of mercury. What is the vertical height of mercury? 40 cos 30, right? Vertical height of mercury is, it is 40 cos 30. 40 cos 30. We get 40 cos 30. Clear? 40 cos 30. Like this you can get the answer. Okay? In mercury centimeters. Let's go to question 4. Question 4. I have asking the location of the match for to be specific. No idea actually. We'll let you know, but it really should be somewhere close. And there was another one. We need face painting. How was it? Okay. Question 4. Okay, pay attention everyone. So in this case, a container is inside water. It's inside the water column, not a water column inside a pond or something like that. But a gas column can remain. Some amount of gas can remain if there's enough pressure, right? If there's enough pressure, okay? Some amount of gas can remain here, right? So they are asking if this is 30 and if the pressure in the vessel is 1 into 10 to the power 6. If the pressure in the vessel is 1 into 10 to the power 6, what is the air pressure above the water here, P naught? Clear? So what is the idea? If the pressure here is 1 into 10 to the power 6, that's what felt by this liquid level, this level. So in the same liquid at the same level, you have the same pressure, right? Clear? That means outside the container here, you have the same pressure. Clear? Outside the container at the same level, you have the same pressure. Clear? So I'll write 1 into 10 to the power 6 as P. Then this is P. Here you have P naught. So P naught plus H rho G equals P, right? P naught plus H rho G. P naught plus H rho G equals P. Clear? P naught plus H rho G equals P. So here we have to get P naught. P naught equals P minus H rho G. Pay attention. P naught equals P minus H rho G. What is the pressure P here? 1 into 10 to the power 6. Then it is 30 meters of water. So minus H rho G. It's 30 meters of water. Rho means the density of water, 10 to the power 3. Rho means the density of water, 10 to the power 3 into G. Now here don't use mercury centimeters, okay? This is not mercury, this is water, okay? Don't mix things up, okay? You can't use any mercury centimeters here because this is not mercury, this is water. So it's easy to go with Pascals, right? So it is 30 rho G, H rho G, clear? What is the answer? It's 7 into 10 to the power 5, right? Yes, right? 7 into 10 to the power 5. So it's 7 into 10 to the power 5 of Pascals. Third one, here it is like this. This is the water level, this is the level in water. It is 5 meters here. It is 5 meters here. So still the pressure inside the vessel is 1 into 10 to the power 6 pascals. That means P, if the pressure here is P, pressure here is P, then the height here is 5. So if this is atmospheric pressure, P naught plus H rho G, P naught plus H rho G equals P, okay? It is P naught plus H rho G plus H rho G equals P, clear? So P naught equals P minus H rho G. Again, P is 1 into 10 to the power 6. P is 1 into 10 to the power 6 minus H is 5 meters. From here to here, it is 5 meters. Rho is 10 to the power 3. G means 10. This is the answer in pascals. Let's go to question 7. Here. So today's content is quite easy. Can't avoid that because it's in the syllabus, so I can't skip that part. From next week only we are learning the new content. Actually new content, but still next week also we have to learn Archimedes. So many content would be familiar until we move to hydrodynamics. Okay, there you have Bernoulli, how planes work and everything. There you have a set of new content, but hydrostatics is actually same as O levels. Okay, here as shown in the figure, the object is balanced on a right arm of this device. What is the pressure at point B? What is the pressure at point B? If the density of water is 1000, A and B at the same level, the mass of the object is 100, the cross-sectional area of the tube is 100 centimeters squared. Okay, so it's quite simple. What is the pressure here? What is the pressure here? It is weight over area, right? Pressure here is, I'll take it as P1. It is the weight over area. Here. Then from here to here, it is that plus H rho G, right? It is that pressure P1. It is that here the pressure P2 is, here the pressure is P1 plus H rho G. Clear? It is P1 plus H rho G. Clear? P1 plus H rho G. Then in the same liquid, in the same level, you have the same pressure. Okay? In the same liquid, in the same level, you have the same pressure. Okay? Atmospheric pressure. Definitely you have to consider in this question, okay? In this question, they are not mentioning the value of atmospheric pressure, okay? So if you are using the atmospheric pressure, you can use as 1 into 10 to the power 5, okay? So definitely when considering the pressure here, if you consider the atmospheric pressure, there's an additional of 1 into 10 to the power 5, but the actual value is 1.016 into 10 to the power 5 or something like that. That means 1 bar. Okay. So like considering the total pressure, you have to write the atmospheric pressure. I mentioned this in the same way in the Sunday class, but still in here, since they haven't mentioned anything about that, I'm just going with the other two sets of pressure. Okay, but the actual thing is you can understand whether they are expecting us to consider the atmospheric pressure or not by giving that in the question. Okay, you can like understand whether they are expecting us to consider the atmospheric pressure or not by like if they mention the atmospheric pressure in the question. But again, since like we started the conversation, like sometimes assume in a huge essay question, they are asking the pressure here. Somewhere in the question, they anyways give the, I mean, when it comes to A levels, we can't judge like this. Why? Anyways, in the beginning of the paper, sometimes they take atmospheric pressure as 1 into 10 to the power 5. So throughout the paper, we have to consider that the atmospheric pressure is given. Okay. So we can't decide what to do. But sometimes you may see in questions they ask not the pressure, the hydrostatic pressure. Or sometimes they ask the pressure by the water column. So in that cases, sometimes I can't tell for sure. Sometimes they are expecting the hydrostatic pressure only. Okay. So we have to check the words and all. We'll see when we are doing questions how to handle that. Because always we have that doubt whether we should consider the atmospheric pressure or not. In this one, as he mentioned, obviously if this is atmosphere, there is atmospheric pressure. Okay. But ideally we don't know whether this is the atmosphere or what is the setup. They are not talking anything about the atmosphere, right? So that's why I'm going with these two only. But ideally, instead of giving a setup like this, okay, if this is something happening in a vehicle, like these kind of systems, they are in the vehicle hydraulic systems kind of stuff that actually if this is in an environment that the atmospheric pressure exists, we have to definitely get the atmospheric pressure. But sometimes you will see this word, okay, get the hydrostatic pressure. Okay, sometimes you will see that word, get the hydrostatic pressure only. Or sometimes you will see, find the pressure by the liquid column. In such cases, they are expecting only the pressure by the liquid area. Okay, moving forward. So here it is P1 plus H rho G. It is P1 plus H rho G. So we have the same pressure at the same level. So PB is equal to P2, which is P1 plus H rho G. P1 is mg over A plus H rho G. Okay. So if you are in doubt in essay paper, okay, what you should do is just write if the atmospheric pressure is considered and write the answer again. Okay. If the hydrostatic pressure is considered, then PB equals mg over area plus H rho G plus P naught. Clear? So what are the values? It's 100 kilograms. 100 kilograms, so 100 into 10 over area. What is the area? 100 centimeters squared. Area is 100 centimeters squared plus H rho G. What is the height? Height is 20 centimeters. Rho, density is 1000. Density of water is 1000, 10 to the power 3. H rho G. G means 10. This is the answer in pascals. Clear? This is the answer in pascals. So we get, after solving this, we get 102,000 pascals. Okay. And like our 28 class dates were released. It's on Tuesday. Pay attention. It's on Tuesday evening and Monday evening. Entirely English medium one is in Tuesday evening and other one is on Monday evening. Okay, so the messages are passed in the group. So if possible, please pass the message. Okay, if possible, please pass the message. All the posts were released in the group. Pay attention. Stop talking. So all the messages were passed in the group. So if possible, pass the message. Anyways, our classes go in that usual curve. In 27 batch also, we started with like 200, 300 students, dropped to 100 by the second day. Then we again reached like 600, 700 in English medium. So that's how it goes every year. But I mean, I wasn't able to stop this for years, okay? So every year it happens, we start with 200, 300, drop to 100. After like 5-6 months, we again grow to 600, 700 when in English medium. In Sinhala medium, it's quite different. It's quite complex, but I usually, I mean, to be honest, I actually like teaching in Sinhala medium than English medium because, not because of any specific reason, there are very good Sinhala medium teachers, like a bunch of teachers that we respect a lot. So there's a huge competition in Sinhala medium, and whenever there's competition, it's fun. So in English medium, I don't see that. So, I usually like to maintain a Sinhala medium class parallel with English medium because it helps me grow. Because I have to compete with all the good Sinhala medium teachers. Competing with them, I watch their videos every year, every day. I mean, when I'm going on treadmill, I watch Sinhala medium teachers recording sometimes. Sinhala medium in the sense, not very younger people, very senior people. Like there was a lot of extremely senior Sinhala medium teachers in physics with a lot of knowledge. That means some of these people are dead actually by now. Okay, like there were teachers specific for, pay attention. There were teachers specific for different topics. That means for electrical, this, for mechanics, this one, for static electricity, this one. There are Sinhala medium teachers like that, very senior people. So I usually watch their recordings always because I have to grow. I can't do that in English medium, obviously. Okay, so that's why I usually maintain a Sinhala medium class too. So if possible, pass the message, okay? If possible, pass the message. The classes are on Tuesday evening and Monday evening. Yep. So moving forward, pay attention. So as usual, we are gonna skip the practicals. Pay attention. We are gonna skip the practicals, but pay attention, everyone. Stop talking now. As usual, I'm going to skip the practicals, but one thing is, if there's anyone who's getting these practicals for their upcoming term test, maybe next week, maybe the week after that, just let me know after the class. I'll provide the recording of the practical. Okay, I have a separate recording for all the practicals. I'm not going to provide the recording for the class. I'm just doing that in the class. But if you're getting this for your upcoming term test that you have in next week or the week after that, let me know. I'll provide the recording, okay? So let's move forward. So I'm going to skip the practicals with exercise 3. Okay. Pressure transmission principle or the Pascal's principle. Okay. So what is this pressure transmission principle? You know that if you take a liquid system, okay, if you take a system of liquid, if you increase the pressure from one side, what happens? Pressure in the whole system increases, right? If you fill water to a balloon and if you try to press it, it will expand in other areas, right? Why? What is the reason for this? This is the pressure transmission law. That means liquids have a property that is, if you try to increase the pressure at a certain point like this, you apply a force and try to increase the pressure at a certain point, that additional pressure is felt by all the surfaces associated with this liquid, okay? That additional pressure is felt by all the surfaces associated with this liquid. That means you give some additional pressure to a liquid system, okay? You give some additional pressure to a liquid system. That additional pressure is transmitted throughout the liquid, clear? That additional pressure is transmitted throughout the liquid. We call this the pressure transmission law, okay? Pressure transmission law actually by Pascal, okay? So what is the reason for this? And why liquids? What is the nature of liquids? They are incompressible, okay? That's the reason why. Since they are incompressible, if you press them, they try to expand from somewhere else, right? Clear? Since they are incompressible, they can't reduce their volume. So if you give a pressure, if you give an additional pressure, it tries to expand from somewhere else, right? It tries to expand from somewhere else. So due to this requirement of expansion from somewhere else, the pressure is felt by all the surfaces in contact with that. So recently also you may have seen examples for this. Sometimes a landslide happens here, okay? Sometimes a landslide happens here. Landslide happens here. Somewhere close to water. There are lands, okay? There are lands like this. Due to this landslide, all of a sudden, a flood appears, a small or some kind of impact or a flood appears, or sometimes some houses get damaged, sometimes 100 or 50 or 300 to 100 kilometers away. Why? Many of our constructions are placed on marshlands. That means although there's land here, okay, although there's land here, what is this? It's a huge water body underneath, okay? Huge body of water underneath. Although you can see a land here, it's a huge water body underneath. Then what happens? Pay attention. Then what happens? If this landslide creates an additional pressure, and if additional pressure is felt by the water, that additional pressure is passed or transmitted throughout the water column going underneath the land, okay? So then whenever there's an opening, the water tries to expand, clear? So in 1 year, I think 2014 or 2016, they asked this in A levels too, okay? They gave the same scenario then and asked, what is the reason for this, okay? Lot of students mentioned some different answers. That was one of the lowest performing MCQs, okay? The reason was it's the Pascal's pressure transmission law, okay? That means the pressure is transmitted throughout the system, okay? Pay attention. Pressure is transmitted throughout the system when an additional pressure is given to a certain point, okay? Clear? Now, this is what happens in a, pay attention, this is what happens in a hydraulic system. What are the examples? You have seen systems that lift vehicles, okay? Systems that lift vehicles, okay? We apply a force here, okay? This is a water body, water or some kind of a liquid, okay? Then when you apply this force here, if the area is A1, if the force is F1, if the area here is A2, okay, what is the pressure you apply here? You apply a pressure of F1 over A1 here, right? Clear? You apply a force pressure of F1 over A1 here, clear? The additional pressure here is F1 over A1, clear? Additional pressure here is F1 over A1, clear? Clear? That additional pressure is transmitted through the system, but this is where the expansion possibility happens. So as a result, this water body will push the vehicle up and move up, clear? So by the same pressure, that means the pressure given here is equal to the pressure given here, which is F2 over A2, clear? Pressure given here is equal to the additional pressure felt here, clear? Additional pressure given here is equal to the pressure felt here. So F1 over A1 is equal to F2 over A2. So as a result, you can write F2 equals F1 over A1, F1 over A1 into A2, clear? F1 over A1 into A2, okay, clear? So now what you can do is, if A2 is way larger than A1, you get a higher pressure, higher force than you provided, right? See, if A2, stop talking, if this A2 is larger than A1, if this A2 is larger than A1, you get a higher force out than you gave to the system. That means if you apply 100 newtons here, okay, if this area is 200 centimeters squared, if this area is 20 centimeters squared, F1 force is 100, A1 area is 20, A2 area is 200, you get what? You get 1000 newtons out, okay? You get 1000 newtons out. Got the idea? You give a small force, but you get a larger force out, okay? Same thing happens in the hydraulic jack in your vehicle, okay? That means when we try to lift the vehicle a bit, okay? You have the hydraulic jack system, and at the same time your brake system, not the modern electronic brake system. The old brake system, you have the same scenario. What? Pay attention. In the previous brake system of a vehicle, you have the same thing. That is, this is a liquid column trapped. Okay. This is a liquid column trapped. Okay. And what happens is, here you apply the force. Here you apply the force. Okay. Only. Here you apply the force, okay? Here you apply a force. That additional pressure is transmitted to these two discs, okay? They would try to stop the wheel, okay? They would try to stop the wheel, clear? Okay, there are questions under all these examples, so you will understand it better when we are doing questions, okay? What happens is you apply a force here. The pressure is felt by two discs, okay? They come closer, they compress the wheel, stop the wheel from moving, okay? Stop the wheel from moving, okay? Then in this scenario, okay, this is Pascal's pressure transmission law. Someone may think, okay, wow, this is nice. Why? We do a small work but get a larger work out. See, we do a small work, we give a small force but get a larger force out. That means by a small work, we get a larger work out, which means this is an energy production mechanism that way. If we are giving a small work and getting a larger work done, in a way, this is an energy production mechanism. This is not an energy production mechanism, okay? Why? What actually happens here is, now think, this is 100 and this is 20 centimeters squared. This is 200 centimeters and we get 1000 newtons, okay? Now tell me, to move this by 1 meter, how far should you push this? How far should you push this? It's the same volume of liquid, right? It's the same volume of liquid. So if this goes up, the volume of liquid that goes up, the volume of liquid that goes up is 200 into 1. 200 centimeters squared into 1. It is 200 centimeters squared into 1. Okay. So whatever the water volume that goes up should go down here, right? It's the same volume of liquid, clear? Whatever the water volume goes up here should go down here, clear? So what is the water volume going down here? What is the water volume going down here? It is 20 centimeters squared into x, right? It is 20 centimeters squared into x, clear? Which means 20 into x, you get 10 meters. 10 meters. That means to move this 1 meter up, you have to move this 10 meters down. So then what is the work done? Work done is Fx. Work done is Fx. Here what is the work done? 100 newtons into x. That means 100 newtons into 10 meters. Clear? Here what is the work happening? It is F2 1000 newtons. It is F2 1000 newtons into 1 meter. It is 1000 newtons into 1 meter. Anyways, you get the same work. See? 100 newtons into 10 meters equals 1000 newtons into 1 meter. So this only increases the force, okay? Understand things properly. This only increases the force, clear? You give a small force, you get a larger force out, but you are doing the same work, okay? With this, I mean, it's quite convenient. Why? For us, giving 1000 newtons is difficult, but we can give 100 newtons, but we are okay with pushing this 10 meters down, okay? Pushing this 10 meters down is way better than trying to give 1000 newtons. So from our side, we are giving a smaller force, but pushing this 10 meters down. But we don't need to lift the vehicle by 10 meters. We need to lift it only by 1 meter. So the system gives us a larger force, but smaller distance. Here we give a smaller force, but a larger distance. Clear? So it's the same work input is equal to the work output. Same energy input is equal to the energy output. Clear? Same work done. So this is not an energy production mechanism. Okay? This is not an energy production mechanism. Whatever the work we do, we get out. Okay? Only the force is transferred. You knew a similar mechanism like this in grade 7-8. Somewhere like grade 7-8. What is that? Lever systems. Lever systems. Can you remember? You had different types of levers too, right? It's not in all of us, right? 3 types of levers, you had this kind of stuff, right? Somewhere you had this. I mean, I learned means you have learned, okay? I mean, for sure it wasn't in the university, so that means somewhere with you guys. I mean, grade 8, 7, 9, somewhere like that. Yeah? Yeah, this was there. You had, you had lever systems somewhere, grade 8 or 9 or somewhere like that, right? I mean, you had lever systems like it's balanced here, or it's balanced here and the force is provided here, or it's balanced here and the force is provided like this and the object is here. Okay, you had this kind of stuff. Lever mechanism is also a similar thing. By giving a small force, according to the lever system, you are getting a larger force out, but the work done is same. Okay, clear? Okay, so you can try and finish. You can try and finish exercise 5. Okay. So there's only one topic left in hydrostatics, that is upthrust. Okay. There's only one topic left in hydrostatics, it's upthrust. Archimedes law. Then we are done with hydrostatics. So pay attention. Next week, by next week, finish exercise 5. I'll start with exercise 5 questions. Finish it. Then let's finish hydrostatics, and we can finish hydrostatics by next week and start doing proper questions. Okay, thank you. And write papers. Okay, write papers. No matter whatever the mark you get, please write papers. Keep writing the papers. Thank you.